So this session title is Recent Advances on the Standardization of the MPEG Video-Based Dynamic Mesh Coding VDMC, and it is presented by Patrice Rondao, Principal Standardization Specialist at Nokia. Patrice is a Principal Standardization Specialist within Nokia Technologies. He received his MS in Electrical Engineering in 2002 and his PhD in Applied Sciences on perception and resynchronization issues for the watermarking of 3D shapes in 2006 from the University Catholic de Leuven, Belgium. For 12 years, he has been Senior Research Engineer at Nokia Bell Labs. He actively contributed to topics such as interactive and immersive video streaming, compression of 3D representations, meshes, point clouds, multi-view plus depth, 6DoF view synthesis, and real-time 3D volumetric video capture. He is currently leading Nokia's research efforts on the standardization of the MPEG video-based dynamic mesh encoding. Published more than 40 conference and journal papers, and he is the senior member of the IEEE Signal Processing Society since 2015. Awesome. So, Patrice, welcome to the stage, and the session is all yours now.
So yes, indeed, my name is Patrice, and I'm going to talk about VDMC. It's the coding of dynamic meshes based on video codecs. It's standardization work that is ongoing at MPEG. And we'll see that the type of dynamic meshes we're coding are type of photorealistic avatars. So we will go more into detail into this presentation about that. Let's go to the next slide. So this is the outline for this presentation. We'll look at 3D and volumetric compression at MPEG as an introduction, and what are meshes, dynamic meshes in our case that we are dealing with in VDMC. Then the core of the presentation will be about VDMC, how it works, on what specific tools it's based on, what are the main principles behind it. And we will have a brief review of its performance, and then we will have, I hope, some time for questions at the end of this presentation. So to start with, I'm sure you're all you all know. Oh, sorry about that. You all know MPEG and its success story about audio and video codecs. We all used MP3s, MPEG-2, MPEG-4, AVC, HEVC are a few names of codecs that have been widely deployed and available on a number of devices. But actually, MPEG is not only about audio and video, but also has an impressive record track of standards related to 3D. And we have here works that have been done since the 98 on MPEG-4, for example, already including 3DMC as a mesh codec and face animation into MPEG-4 Part 2. And here I picked only a few of the standards and different amendments that have happened between 98 and 2011. Interesting names for the rest of the presentations are, for example, the animation framework extension AFX that brought improvements on the previous standards on geometry, appearance, and animation compression. And then in 2008, FAMC had some traction with its improvement of compression for frame-based animated mesh compression. And 2011, scalable complexity flavors were added as an amendment to this AFX into MPEG-4 Part 16. There were other amendments after that, but let me move to when MPEG started to look into MPEG-I for MPEG Immersive. I skipped a few points, for example, for 360 video, but I think things started to be interesting, at least subjectively, in terms of when the CFP on point cloud coding started. MPEG looked at how to encode point clouds, different types of point clouds, from dense to sparse point clouds. And actually, very surprisingly, video codec based approach has outperformed the state-of-the-art all geometry-based approaches for encoding dense point clouds. And this was the birth of V3C and VPCC, so the video-based point cloud coding. I'll go back to how this works. And you see these are typical point cloud-based avatars. While sparse point clouds, such as those you get from LiDARs, didn't work well with video-based approach, or the other way around. Video codecs don't compress those approaches, those type of LiDARs data very efficiently, and a geometry-based point cloud coding standard was recently released for those types of point clouds. At the same time, still this year, MIV became also international standard and has been designed in a very similar way as VPCC. So we'll come back to that in the next slide, but it's also V3C based, so it's visual volumetric video coding. We use a set of projections in these two standards for point cloud coding or for multi-view plus depth type of input. And these approaches have outperformed the state-of-the-art at that time for this type of content. So in MIV, typically the content is captured from a set of cameras, and the representation provides the user the possibility to freely move into the scene in a given viewing space and see the content being captured from various angles. So you can see MIV as capturing the environment from a set of cameras with texture and depth information, and VPCC being more focused, at least on the test sequences that were used, on dynamic point clouds, for example, this type of photorealistic avatars we can see here. And based on these interesting outcomes from video-based approaches for 3D volumetric content, we started at MPEG looking into the coding of dynamic meshes as an extension of this visual volumetric video coding standard. So just to give you a glimpse on how a video codec can help or can be used to code 3D information, actually it works by, in this example for point clouds, you perform a first 3D segmentation of your point cloud into 2D local dense patches that you will project on planes, and you will compose a 2D atlas based on that. That's what you see here, within white points that corresponds to the point clouds that are projected on a 2D atlas. And when it's black, it means that this pixel doesn't correspond to projected information from the point cloud. And two video components are attached to this atlas. The geometry, which gives you the depth of each point compared to this atlas projection plane, and color information, typically texture information. Here, the fancy colors help you to see the correspondence between those patches in 2D in the atlas and the patch on the 3D shape. And actually, the V3C standards covers the atlas metadata, all the information that tells you how to reconstruct the 3D information from those 2D patches and how to read those atlases, and the decoding process. That's what the V3C standard covers. And these video components, actually, they are encoded using video codecs. And here you have an open choice between, for example, AVC, HEVC, VVC, or if you want AV1. When I put this star on open, it's the codec you use needs to be registered as in the MP4 array. We'll come back to that later. But this freedom actually helps you to still improve the compression performance without updating your V3C standards. If a new video codec arrives with improved compression performance, then you can use it within this framework. So the coding gains were for both VPCC and MIV impressive, actually, compared to the state of the art. And on top of this, using video codecs that provides you hardware acceleration on mobile devices, because most of the mobile devices have chipsets that have hardware support for decoding those video codecs. So there are these two aspects that make V3C extremely interesting for deploying this type of approaches of volumetric data. And this explains the current success for dense point cloud coding and multi-view plus depth coding using video codecs. Based on that, the group looked at dynamic mesh sequences and explored through a call for proposals how to possibly extend these type of approaches to dynamic meshes. And actually, there's a slight difference between these dynamic mesh sequences and point clouds or multi-view plus depth. Of course, there is something in common. It's the fact that you have geometry, you have points and 3D coordinates. You have also attribute information, such as colors or textures. But on top of this, for each frame of this dynamic mesh sequence, you have connectivity. You have triangles, edges that connect those points from your geometry, and that give you this piecewise linear approximation of the surface you're representing. And compressing this combinatorial information with video is slightly, let's say, less obvious than compressing geometry or attributes, as we have seen for point clouds and multi-view plus depth. And here on the left, you see one of these sequences we are coding at MPEG. It's called Mitch. And here's another one, another thing related to these dynamic mesh sequences we are dealing with is that the connectivity in this case may vary from frame to frame. So we have set no constraints on having the same number of triangles and corresponding vertex IDs from frame to frame. So this is more general, can cover more capture cases, but this is also more challenging in terms of motion estimation, of course. On top of this, the UV parameterization you may get as content may also not be stable from frame to frame. And just for the sake of the clarity, UV parameterization is that for each point of your mesh, we associate 2D coordinates, so UV coordinates that tell you what pixel in the texture maps corresponds to that point in your mesh. So that's how you attach the texture information to your mesh representation. So this is the 8 sequences we are using in dynamic mesh coding. You can see on top or bottom of each of these footage from which Capture Studio they came from. And you also have some details. I won't go to listing all the numbers that are there, but you get a glimpse of what kind of texture resolution we are dealing with, so 2K by 2K or 4K by 4K, and typically we have a number of vertices or let's say the number of faces, about 40K or 30K for some of these sequences. And as an example of target bit rates that we are aiming at for this type of content, for lossy compression, we reduce this raw format of 1.5 to 4 gigabit per second to 4 to 21. depending on the type of the sequence, it can be a bit lower or more. But that is one example for one of these test sequences that we can reach high quality already around 20 megabit per second. For this type of content, this type of resolution, and mesh resolution as well for 30 or 25 frames per second. So that being said, let me go to how VDMC was built, and it was actually chosen as the winning proposal of the CFP that was raised for dynamic mesh coding, became what is now VDMC, and that we are working on at MPEG. So Apple won this CFP with an approach that is based on subdivision surfaces and video coding, as in V3C. So we'll see how it works. And I inspired myself from their own slides for this one. So the original, let's say, for explaining subdivision process for surfaces and for meshes, it's simpler to work first with 2D polylines to give you a glimpse of the idea. Let's say this blue curve is the original with the different points attached to it. The first step we will perform in VDMC is to simplify it or decimate it to a coarse representation that is simpler to compress. That takes less bit rate to represent. And you see that typically we remove points that iteratively, in a way that the shape is relatively preserved compared to the original with this simplified version, but the number of vertices is importantly reduced. Typically a target can be between 5% to 20% of the original mesh. Then the next step is to subdivide this coarse representation by iteratively adding vertices in the midpoints of these edges here of the polyline, of the simplified one. So here you have 2 iterations of this process between each of these vertices from the coarse simplified representation. We add the midpoints and so on until we reach the desired level of subdivision iterations. And at these steps, you see we haven't added any information. It's a pure interpolatory approach. We actually tessellate further the polyline here that we got from this simplification step. Now we will approximate the original surface by adding displacements. So we will displace this polyline here that is subdivided to approach as much as we can the original shape in blue. These displacements, they may be aligned with the normal direction of the current segment that you have here in your subdivided shape. And they can be then 1D. The information then we need to encode is this simplified version of the mesh, the number of iterations we perform, and then these displacement vectors that we need to encode. And the goal is, of course, to make sure that the displaced curve in green is the closest as possible to the blue one. You may observe that the number of vertices may not be the same with this process. That's one of the characteristics of this subdivision process or multi-resolution for meshes processes. So we saw that for polylines. This is what we get for meshes. So here is the original represented in wireframe with its UV parameterization. We go through a first step of simplification that reduces the number of meshes, the triangles of the mesh. So you see we also perform reparameterization for this mesh. It's a detail, but that explains why it's not exactly the same image as here. Typically for simplification, you can use whatever you want, but in our test, we are using the quadratic error metric from Garland from 98, I believe, already to perform that. And then the subdivision step is very similar as for polylines and for meshes. For every edge, we will add a midpoint, and as you do that for every edge of your mesh, you see that you're multiplying the number of triangles by 4 at each iteration. And so typically we use 2 to 3 subdivision iterations, and you see you have a very dense mesh here that is displaced. The error vectors are already added to the representation here, and you see that the parameterization, the UV coordinates, are also subdivided compared to the simplified version. And so if you compare the original here with the displaced there, you see that with several fitting operations, the wireframe here, which is the original, is close to the displaced surface that is represented here in flat shaded. So the interesting part of basing this work on subdivision is that we are able to create a set of level of details for our meshes. So that is interesting when you want to render your avatar from close or to a distance. You want to be able to play with these different resolution and LODs of your mesh. So that is available for free with the representation that VDMC uses, if I may so. And the fact that we have hierarchies of mesh resolutions, we can use that to reduce the information for displacements using the so-called lifting scheme or lazy wavelets on meshes. So this simply is a hierarchical scheme that will predict the geometry, the displacements from the higher LOD based on the lower LOD. And this enables you to actually, although you have more and more displacements at each level of detail, the size of this displacement of these error vectors becomes smaller and smaller. And so the amount of displacements you need to encode for the last iteration or the last LOD is very sparse. A lot of these vectors can be easily quantized, and despite the fact that we multiply by 4 at each iteration the number of triangles, actually the amount of information that needs to be transmitted as details of the geometry is greatly reduced thanks to the lifting scheme. Then we didn't talk about motion, but actually what we do is that we implement the motion estimation on the base meshes in the current VDMC encoder tests. And for that, you can use codecs that will already exist for encoding the motion. So for example, FAMC could be a choice for that, or develop your own, of course. And we handle everything related to the temporal aspects of animation is handled in the very same way as for video codecs in V3C, so that we'll see that later on. The videos and the animation aspects are well aligned. And I'm not sure I have enough time to go into the detail, but basically you may want to code the motion vector for a given vertex based on the previously coded motion of their neighbors. And it is only an error vector, again, like displacements for the geometry that you need to encode. So this is what we typically use now for the base meshes. And one way, when your connectivity is not the same from frame to frame, you have some heuristics to make sure that the base meshes themselves are align in terms of resolution, so that you can more easily apply those animation codecs to them. So these are more encoder strategies. But that being said, as V3C was VPCC and MIV were relying on the video codecs for the texture and the geometry, you can rely as well on animation codec for the motion aspect for the base mesh part. So recapping what we have said so far, if you remember, we went from the original to a simplified or decimated version through a simplification process. And then we have the subdivision that creates a detailed version and displacements to get a shape that is as close as possible from the original. What we end up with as representations that we need to transmit and to encode is first a base mesh. So one part is the coarse geometry and connectivity. That you can encode with a mesh codec. For example, Draco is one option. We are also working on another edge breaker implementation at MPEG for that. And the motion compensation, the animation data, that can be compressed with a motion codec as well. The displacement data organized in level of details can be predicted with the lifting scheme, as I explained, and packed into video frames. So that might be counterintuitive, but these displacement vectors can be turned into scalars, can be packed into a video frame that is then encoded with a video codec itself. And for the texture, it is also to be coded with a video codec. So as for V3C, VPCC, MIV, we end up with metadata that explains you how this process was performed and how to reconstruct the 3D information, and a set of codecs you can choose to compress the different video components related to your mesh, dynamic mesh representation. This enables to get the best compression performance out of these codecs into VDMC. So this is how a bitstream looks like. For VDMC, you have metadata that is an extension of V3C, describing all the process and the different parameters that are to be used in the decoder. You have the base mesh, the animation data, the displacements, and the attributes as video components. And here you can see the decoder as different tracks to reconstruct the video. And then you have the base mesh decoding process with here a switch between intra and inter, where you have the static mesh decoding process, the motion decoding process, and the inverse quantization of that base mesh. And here, what you do is you unpack the displacements, apply the inverse with a transform, and so you're able to attach your displacements, the reconstructed displacements, to the reconstructed base mesh and obtain your detailed mesh there and the attached texture. So that's in a nutshell what's going on here. What is interesting, and here again, I inspired myself from this work from Apple. This base mesh representation is the only part that is, for the moment, requires a CPU implementation to be decoded. But all the remainder can use hardware acceleration for the video coded parts, for example. And the reconstruction, post-processing, and rendering can stay on the GPU. So here you see the type of intercommunication between CPU, GPU shaders, and the GPU ASIC for the video decoding themselves. The idea is to turn this as the lightest as possible, or to implement it to the GPU, but this design was thought to be deployed quickly on the market with a GPU supported implementation. Of course, VDMC is still in standardization process, so too early to have real-time codecs yet, implementations of VDMC, but that's what we aim for, and we are working on for the moment. So let me touch about performance. This is what we get in terms of bitrate analysis. So you have 5 rates here for long dress that you can see here with different target bit rates. So from 5, a little bit less than 5, and 22 for the highest the highest bit rate. And you see that metadata is minimal, and the bit rate is mostly related to the texture and the displacements. So it's it can be nicely accelerated on hardware implementations of video codecs. So that is an interesting aspect of the VDMC design. You don't have that if you use Draco. If you use Draco for the connectivity and the geometry only, and then encode the texture at the similar rates, then you see that because Draco works on CPU, you have a 50-50 balance for the highest rates, but otherwise you cannot really leverage hardware acceleration for the video codec part. So that's what VDMC brings on top of having motion compensation and level of detail. Then in terms of objective metrics, I'll go very fast, but the blue curve is VDMC. The red one is the anchor that was Draco, and you see that the higher the better. And so VDMC outperformed for these 4 quite nicely the Draco-based anchor. So the anchor is the reference you need to outperform in the CFP of VDMC. And the subjective assessment that were performed after the CFP responses that were made at the beginning of this VDMC standardization process, you see that the winning proposal that has become VDMC was reaching mean observation scores that were the highest compared to Draco here in black. And so scores above 8 in mean observation scores mean that the quality is already excellent or difficult to spot any differences with annoying details. I mean, between 7 and 4, the quality is described as fair. Below 5, it's not good. So you see that you need about 10 megabit per second for this sequence here, basketball, to get very good quality. This is an older version of VDMC. It was made at the time of the CFP response, and now it has been improved for almost 1.5 years. The performance is expected to be even better than that. So let me. Yes.
Yeah, quick reminder, you have 3 more minutes.
Yeah, sorry to take so long. So let me quickly conclude. This VDMC standardization efforts are ongoing, and the time frame for the final draft international standard is end 2024, start 2025, around those dates. And quickly recapping, VDMC builds upon 30 years of 3D compression video coding research, leveraging the best of these codecs and having a smart design that leverages hardware GPU considerations in mind for fast market adoption. It is designed with levels of details. It is an extension as VPCC and MIV of V3C, so relies on these video codecs as well, but mesh and animation codecs as well. The type of content we are dealing with are photorealistic avatars, of course, represented as mesh sequences. There are other representations of avatars, of course, but this is the type of information we are compressing. And that's what I wanted to share today. So I'm welcoming questions now. Thank you.
Thank you, Patrice. It was a really detailed presentation. Learned a lot of stuff. So thank you for all the information. Since we are short on time, so anyone who wants to ask any questions, feel free to unmute and ask your question. Yeah, Walter Ventures. I don't see the name. It's Scott. Yeah, please unmute and go for the question.
Oh, yes. Hi, thanks. Terrific presentation, Patrice. My question is about the encoding of the textures. Would this enable video data to be applied to an avatar, for example? So you could put like, an animated video on somebody's t-shirt, for example, or something more sophisticated?
I'm not sure I really understood your question. See, if you were asking that a video texture could be mapped to an avatar, right?
Yeah, is that what's happening, or is that?
Yes, it is. So for every frame, you get a mapping between the vertex and the UV coordinates of the texture map, and that's how the video is mapped onto the mesh at each frame.
So her dress could be completely psychedelic, swirling colors, anything like that.
Oh yeah, if you would like to change the texture in a meaningful way, I mean, you could definitely edit it. Yes.
Right. And following that, is there savings to be had then for static, for the static dress? Is there savings to be gained then by reusing the texture rather than replacing it all the time? How does that work?
All right. I see better. You were talking about static texture versus video texture. I'm sorry. Yes, you could reuse that. The video codecs are extremely efficient in handling the redundancy that you have between frames. So if you have a static texture, I mean, for every frame, the video codec will compress that extremely efficiently. Now, what will be different is how you implement that on GPU, that you're sure that the data is copied or cached. But that again, there are ways to optimize this indeed.
Awesome, thank you.
Yeah, thank you, Scott, and thank you, Patrice. We are out of time. So for folks who have additional questions, please stay back. We will stop the recording and there will be a water cooler session.